Hey guys, Joe Pye here at Advanced Innovations. Welcome back to my shop. You know, this demonstration is going to be about rounds and angles as they apply to both the lathe and the mill. So whatever your passion is, hang around because I'm going to bounce back and forth between the applications for both of these. But this is going to be about geometric construction standards that will take a lot of guesswork out of the work that you do. Things that you should just lock away and say, this is the way it's going to be forever, and my life is going to be easier because I know this. So my life will be easier if I could find my marker. There we go. All right, here we go. Let's start with the lathe part. And I'm only going to draw just a basic profile of this, and there's a reason for it, so hang in there. You got a turn diameter to a specific length, right? That's what the engineer wants right there. And 45-degree angle. I bet that's pretty close to 45. And out. Now after he does his finite element analysis on this, he's going to say, can't have a sharp corner right there because it's a crack point, so let's put a giant radius on that. And he just says, let's just change the radius. Add the radius. And I'm going to do it with my fancy wooden protractor here. And there's a reason for this. There we go. That's actually pretty good. Alright. Now you got a radius on your part. Wish it was that easy, but in fact it is not that easy. Because now when this changes, it's no longer a matter of just moving the carriage a specific distance, locking the carriage, and then using your compound to single point that out or form tool that out. Now everything has changed. Now the carriage actually, from the time that you face this part off, here, 0, this is how far the carriage has moved before you can start sweeping that angle. So how far is that? What's going on here, and how do we know how to calculate how far everything has moved or needs to move? Well, the one thing that will remain constant forever, and this is the lesson here. You look at the angle that you have here, the angle given on the print. It's going to be on the print. 45 degrees. When you have an arc that blends a conical to a flared surface, it will always be perpendicular to each surface at the tangent point. Here's your center. 90 degrees. All day long. Now, as the pieces start to fall out of the drawing, you start to get little fragments of information that you can actually use. Okay, what do we know? Well, you know the radius of the tool because it's called out on the print. It's probably on the insert that you're using or the form tool that you just ground. So where's the radius here? The radius is right here. Radius here. Radius here. Cool, we're getting there. Let's go with the theoretical projected point here. There's your theoretical sharp corner that they wiped off the print before. This angle right here will always be this angle right here. They will always be the same. Great. Here's the kicker. This point right here, the previous theoretical sharp corner will always cut that angle right down the middle. So now this angle is equal to this angle. Everything is starting to fall out of here, piece of cake. Now the angle, the triangle that you now have, looks exactly like this. If this is 45, each one of these is 22.5. 22 degrees, 30 minutes, or 0.5, but 30 minutes. And the base leg is the radius. And once you have this information here, you take the radius, you multiply the radius times the tangent of the angle. Now the angle is going to be half of whatever's on your print. Okay, 45 is the total. When you split it, you're only looking for this leg right here. So when you split whatever angle this is in half, that's the value that's reflected right here. 22 degrees, 30 minutes, it's half of 45. So now you can see you have all the information necessary to find the bump or the face off and the move before you start to shift. Dimension on the print minus the leg that you just found will give you this distance here plus the radius. There's your total shift. Radius times the tangent of the angle, that angle. Okay, and this little leg right here appears in two places in this formula. It's here and here, since you have two identical triangles. There you go. Let's go with two arcs exactly the same size. Centerline relationship between two arcs, exactly the same size. Okay, now you have two arcs that are touching. What do we know about that? Well, we know that they're tangent, right? That's about all you know. You know what the radius is. And as far as the radius is concerned, one could be a little bit larger than the other. This rule will still apply. If you take the center of both of those circles or both of those round features and draw a straight line between them, tangent point. The centers of the arcs will always be on the same line. Center, center, tangent point, straight line, forever. Construction 101. Okay, let's draw a small one on there and prove that. Doesn't matter what size the arc is, centers will always be on the same line as the tangent. Or should I say the tangent will always be on the same line as the centers. Okay? Another good one to lock away. Good for construction. If you know how to break up these problems that you're having into pieces, all the pieces that are presented will allow you to solve whatever you're looking for. Now this is the core of this particular video. When you have a big radius that has to go tangent into a smaller radius, and that's what I'm going to cut on a rotary table. And a lot of you would early on would look at it and go, I'm going to have to move that part 37 times in order to get that to do that, but you'd be surprised how easy it is. Okay, let's look at the part. Part is square. And for some reason, there's a huge radius on this corner. Kind of ugly, but there's a huge radius on that corner. And there's a smaller radius on this corner. This is what you want to do. Maybe you're making a cam. I mean, this looks exactly like a cam, right? Nice, long sloping rise and quick drop off. I would really like to improve on that, guys, so just bear with me for a second. Kind of defeats the purpose if it's ugly. Still ugly, but close enough. All right. Here's the center of the large radius. And lo and behold, here it comes. Up, 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 up. The center of the small radius is on the same center line. Falls right back to that tangent arc thing. The tangent point is in line with the centers of those pieces. So when you set your part up on the rotary table to cut this outside arc, when you go to make your move, you don't move the entire setup, you only slide the part. You migrate the part, here's the center of the rotary table, you need to pull the part down so that this center is now over the center of the rotary table, and then you continue your arc. So knowing that this construction will hold true forever really does help downstream when you make your setup. Put a rail on, put a stop on, register both sides of the part, something that you can move without losing your mind and moving the whole table and starting over from scratch. It's a lot easier to go from one to the other when you know how that applies Those radiuses are on the same center line this way. All you need to do is slide the part, and you can adjust the size of those radiuses if you slide it in a precision manner, of course. And well, that's what that little alignment tool does that we sell. Works out quite well. Let's go out to the mill, grab a pin, grab a vise, grab a piece of material, clamp it down. Let's cut some rounds. Hey guys, before I get into the demonstration on the setup of this rotary table, gotta show you this new little gadget that I got. This is a multi-axis stop from Edge Technologies. And the thing that I am most impressed with, aside from the absolute quality of the production here, is the adjustability and the range of motion you can get out of this. With all the surfaces rounded like this, everything on a swivel, this can stand vertically and be quite high, or you can literally put the tip of this stylus right down on the table for plate work or whatever. But I use it a lot. I use it all the time for my vise, and when I don't want it inside the jaws or around the vise, I've just mounted it to the outside of the table here, so it's here when I need it. And it's worked out quite well for holding my air hose too. So I leave my air hose dangling from it. And one of the things that I've seen in the past at a lot of shops, and that I've just got to cringe when I see it, is all the little bullet marks and dents and stuff you're going to get on your table from guys throwing their air hose onto the table, and the air hose coming in contact with the casting. Just don't do that. So there you go. If you're not using it as a material stop, use it as an air gun holder, because it works like a charm. So thank you to the guys at Edge Technologies. First class job. If you're looking for one, look them up. Nice piece. Well, to start this demonstration, naturally you want to align the center of your spindle on your machine with the center of the rotary table. And that is most commonly achieved by mounting some type of device to the spindle and rotating the spindle with an indicator on it. Now this is an indical, and let's see if we can make this just stand out. Ultimately something's going to get in the way here, guys. I'm going to try to keep my fingers out of the way. 0, coming around. Let's move back on this side. 0, and 0 in the back. This is what you call trustworthy, right? Now what you want to do when you have an indicator that doesn't move and you think you're saying, hey, this is awesome, grab the indicator body and just bump it back and forth when you're done, just to make sure there is some range of motion on either side of that 0 and you are not pinned, so to speak. Rotate it, all is well. Now this being the recognized way to indicate a rotary table spindle, or align it with your mill, I'm going to show you a second way. And this way is arguably more accurate than what I just showed you. Since you are not technically rotating the mass of this rotary table about that hole, there is other mechanism below this table that this top table registers on. That is your axis. So that's what really should be checked. If you can trust it with that hole, if you've proven it to be true to that hole, then continue to indicate that hole. But just for safety purposes, just for sake of accuracy, we're going to mount a different indicator on here. We're going to check it to the spindle, and we're going to compare the readings without moving anything except the table as the table moves when you use it. And that setup looks like this. I've mounted my indicator to the face of the rotary table. It's a magnetic base. And for those of you that are going to say, gee, what is that? This is a US General Model 387. It is simple. It's just a bunch of laminated plates with some magnets and a few adjusting screws. This is a discontinued item from about 40 years ago, believe it or not. I'm almost ashamed to say that. But what we need to do now is spin the table and watch the indicator, because it's the movement of the table against the spindle that you want to see. This particular table has a release mechanism on it, and this knob right here, if we unlock this, if we unloosen this, there we go, this entire dial mechanism, not just the dial to the graduations, but the entire dial mechanism will move up and out of the way. And when that happens, you can spin this by hand. There you go. So now by rotating this around the spindle, there's movement. There's absolutely movement. Let's go around the back and check it. It's a little closer in the back, so the y-axis is a little bit better than the x. The digital has not moved from the primary setup. Still about 4 out. Come back around. I'm going to be looking for my 0 to come back around just so I know I completed one continuous rotation here. And I should be back on 0, which I am. So the bearing, the rotational mechanism that controls this table, is not true to that bore. Now I have to imagine that the manufacturer of this table probably wants to allow you to cut that bore if you wanted to. So there's an undercut in this top ring. So you don't have to bring your tool or your cutter down and hit this Morse taper ring that's on the inside. You can stay clear of it. So by doing this, I know that when I set up my rotary table, I can indicate the bore close, as close can be, and then put the indicator on the spindle and move the entire table. So I'm going to bump this in till it's true. There's no sense in doing that because I just demonstrated what's going on. And when it's true, we're going to set the vise up with the rail that I have mounted true to the x-axis travel. So let me indicate this and we'll put the vise on. Okay, the initial placement of the vise will be determined by the alignment pin. Once I stick the vise up on there, I'll put this back in. I'll demonstrate 2 ways to, actually 3 ways to use it this time. I'll put the vise up. Slot. And let's put the pin in. I've repositioned the camera around the operator view, so this is looking straight at the front of the machine. And the pin that we're going to use has a 0 face on center and one that's 500 off center. Just to demonstrate the utility of the 500 off center face, when I put this up in the collet, it's a 3/4 collet, I'm going to work with the 500 face. So let's see how that goes. Lock it in. Take the machine out of gear. Going to bring the pin down within the range of the jaw. Visually line it up in my y-axis so that I'm about centered on the pin. That's what I want to do. Let's go handheld for a second so I can show you what I'm talking about. I'm going to try to keep the pin in the middle of the vise. Okay? Digital is still on 0. The machine is still aligned with the rotary table. .350 gauge pin. Excuse me, 350 gauge block. I am going to take that and stick that right in here and pinch it. Now by higher mathematics, if the center of this block connected to the alignment pin is on center at the rotary, on the center of the table, excuse me, on the center of the machine spindle, then this back jaw right now is 850 back. 500 on the pin, 350 on the gauge block. So let's pinch it. And keep it pinched. This is strictly a tool bit. It means nothing. The size is arbitrary. All right, we have a nice solid stack. The spindle is unlocked. It can still rotate freely. I'm going to put an adjustable parallel on the back side of this vise to align the vise true to the table, true to the fence that I have mounted to the rotary table. Let's reposition the camera so you can see how that adjustable parallel works. I did show this in a previous video, but if you didn't have a chance to see that one, it's a good idea to review it. Okay, let's say the vise is no longer parallel with that back surface. And it's only because it's being restricted with the slot in the vise to the bolt to the slot in the table. So the range of motion is relatively restricted. I'm going to take the adjustable parallel. If you've never seen these, they're pretty cool. As you squeeze them, one end to the other, they get higher or lower. And in a pinch, they can come in real handy, especially for something like this. We're going to stick that in there. And in line with the pin, in line with the parallels, we're just going to squeeze it and watch the vise come around. I'm not even going to touch the vise. See the movement? You want to give it a slight little jiggle when you think that you got what you're hoping you got. And this is where I'm going to tighten down my clamp. You will not have to move the vise for the duration of this tangent arc setup, so don't be afraid to lock her down. And I will put 2 clamps on this one. It's not going to be a big cut, but I will position the camera straight up the front so you can see the next step in line, but I'm going to put a clamp on the back side in the meantime. Now that we have the center line of the table on the x-axis exactly 850 to the rear jaw, we want to go on the y-axis 850 out as well. These these surfaces on either side of this pin are 500 from center, so we're going to do exactly the same thing that we did to set up the stationary jaw. We're going to pinch a 350 gauge block or gauge block stack against this face, and then move our stop up against that stack and lock the stop off. That way, at that point, the center line of the machine is going to be exactly 850 into the corner of the part that we will ultimately load on here. And I'm using my nifty little pointer scribe, courtesy of Randy Richard in the shop. If you haven't checked his channel out, go check him out. All right, here we go. We're going to put the 350 stack against this side of the block, because it's 500 from the center to the surface. Another 350 gives me the 850 radius I'm looking for. Just enough to hold them, not enough to damage them. I'll take them out, tighten it down. Double check it, still there. Alright guys, don't forget, if you're going to be doing any kind of profile milling on a part and you're going to be using the top of your jaw as a reference, make sure that your stopper rod is below the jaw, or when you come around with the end mill, you're going to get a wake-up call that sounds like just really unpleasant. Let's throw some parallels in there, throw a part in there, and show you exactly what we've just accomplished. If anyone is having a little difficulty visualizing exactly what just happened, we took the center of the spindle of the mill and positioned the vise on the rotary table so that it is 850 from the stationary jaw on the vise to the center and 850 from the stop to the center. There you go. When I come down with my cutter, I'm going to make an x-axis offset to the edge plus the radius of the cutter, so I know the edge of the cutter is right on the edge of the part. I'm going to climb mill it around to the corner, at which time the long line here will be positioned 90 degrees and sit on the x-axis. I'll get the cutter up off the part. Reposition the part with the 200 block per the demonstration, because that is the difference in the radiuses, radii. And now the part is perfectly in line for the next cut. Let's do it. 850 radius goes first. 1/2 inch cutter. Away we go. $850 plus the $250 on the radius. It's 1.1. .500 diameter cutter, 250 radius, 850 requirement on the part. 850 plus the 250 is 1 inch 100. There's 10 thou left on this table for a cleanup cut, and that is what I'm going to do. So we're going to climb cut this. A lot of people will tell you, you know, climb cuts they grab. Climb cuts do grab, but do yourself a favor and leave a little bit of drag on whatever table axis mechanism you're using at the time, and the drag will probably overcome the desire for that cutter to grab if there's enough drag. So let's make the cut, reposition the part real quick, and go for the 650 tangent radius. Do yourself a favor and figure out which way your table is going to turn before you make the cut. I want to climb this cutter around this in a clockwise trajectory on the part, but that means the part is turning counterclockwise. Don't get confused. Counterclockwise rotation of the part, counterclockwise rotation of the dial. This is how we want to do it. That is a counterclockwise rotation of the rotary table dial. Okay? Counterclockwise. Very superficial cut, strictly for demonstration purposes. Here we go. That was when you add the 200 gauge block. And if all the math is correct, this arc should finish out on this side, tangent to both ends, relatively. Have to remove the spindle as well, so instead of 1.1 we're going to be looking for 0.9 on the x-axis.
see if we can get a better look at this. There is a extremely small dust spot in the center of this. This is a sanded end, guys, so if there's a small flat right there, that will be the reason why. This is not a machined end. We have an 850 radius. You saw the 200 shift on the fly by moving the gauge block into the stop. 650 on the back side. Elliptical, it's not really an elliptical arc, tangent arc, two of them. And that's how it's done. But let's just say that is one of many ways you can do it. And I'll tell you, if you got one of these guys, it certainly is a benefit for a rapid setup.
Alright, well, it's really not all that scary if you have a decent setup and you just make some provisions. A lot of the rotary table work that I've witnessed in the past, there is no XY reference on the table. So putting that rail on the table is a really good idea to just assist you in the positioning of everything. The pin is a great idea. It's a nice little tool to have in your arsenal. And a basic understanding of geometry also helps. Refer to some of the stuff in the body of this video to do the construction and cut a couple of hours off your job. Hope you enjoyed that. I hope you got something out of it. Leave me a comment if you did. As always, thank you for watching. Thank you to everybody that has already purchased those pins. I do appreciate it. And that's all we got for this week. Thank you very much, guys. Joe Pye, Advanced Innovations, Austin, Texas. I'm out.